Hello everyone, my name is Romain Egele. I am a graduate student working with Prasanna Balaprakash at Aragon. Today, I will present you the DeepHyper software during a hands-on session for the ALCF workshop of May 2020. First, I advise you to go on the DeepHyper documentation web page. It's the location when you're gonna find plenty of information about the software. You have information about installations, you have different tutorials, user guides, and developer guides if required. Now, let's start the hands-on session. This session will describe 3 different examples. The first one will be about how to do automatic machine learning with DeepHyper, which means how to automatically search for a classifier, for example, from a scalar. The second part will be how to tune an already existing machine learning model using DeepHyper. And the last part will be how to do neural architecture search with DeepHyper. First, we'll do all of this on our local machine. Then we'll move our project to Theta and run some searches. So right now, I'm in my root directory on my local laptop. I will create a folder for the workshop. I will go to this folder. And from here, I will start my installation. The first thing I'm gonna do is to create a Python virtual environment using Conda. So Conda is required before starting the tutorial. To do so, I'm doing this, and I want to use a 3.7 Python interpreter. Now that the environment is created, I can activate it. And I can see in my terminal, here for example, that this environment is well activated. In order to verify, you can always use which Python and verify the path of your current virtual environment. Now that this is done, we're going to be able to install DeepHyper. But again, before installing DeepHyper, which is a Python package, you have another requirement, which is OpenMPI. So here, for example, I'm on Macintosh, and I can verify with Homebrew that I have the OpenMPI library. Why is it required? Because in DeepHyper, we're going to install the MPI4Py wrapper of OpenMPI. And if OpenMPI is not already installed on your machine, it will not work. So if you have a Mac, you can do brew install OpenMPI to install it very easily. Assuming that this is done, I'm gonna install in DeepHyper using the last version of the software. To do so, I will run this command. Now that the installation is over, we're gonna create a DeepHyper project. First, before doing so, it always good to verify that the package is indeed well installed. So you can run Python and then try to import DeepHyper in Python. Let's verify that we have the good version of the package. And yes, it's working well. From here, let's create a DeepHyper package in order to define the different problems we want to do with the software. So here the package is named DH projects. It's a Python package where we'll define the various problems for DeepHyper. As we can see, the package is well installed. Let's try in Python. And yes, it worked perfectly. Now let's move inside this package. And let's create our first problem folder for the AutoMail example, where we're going to try to automatically find a classifier among some of the Egele classifiers using the Wisconsin dataset. Before doing all of this, it's always good to have a baseline with DeepHyper. This is why we provided a baseline package in the software. How can you try this baseline package? If you execute Python, we can first import the dataset we want. Then we're gonna use the baseline classifier pipelines from DeepHyper. And finally, we're gonna use a basic classifier from Egele. We're gonna wrap our dataset in a load data function following the interface of DeepHyper. Let's try this function. Working very well. Now we are going to define our baseline classifier object. Very well. And now we can execute this classifier with the run function and see an initial accuracy on this dataset. Having a baseline is very useful to evaluate the difficulty of your data and to know and understand if the automatic search with DeepHyper helps you find something improving your baseline. So we know that we want to find something better than 0.95. Now let's create a DeepHyper problem using the command line. You have to be very careful when running this command line because you have to be located exactly here, which means at the root of your package. So if I look at my current path, we created these two folders, you have to be inside the second one with the first init file, which is the beginning of the package. Now we just created the breast cancer subpackage containing these three files plus the init file just to define this directory as a subpackage. Let's open all of this into Visual Studio Code. Of course, you can choose whatever editor you'd like. I'm going again in my project folder for breast cancer, and I have three files. In this first part of the tutorial, we only use one file just to demonstrate some capacities of the software. For now, you can delete all files contained here, and you can also delete the two other files. Just to follow the tutorial file you will have in the same time as this video, I will rename this file as run.py. In this file, I will start to import NumPy. Then, I will import the auto-escalar run function from DeepHyper. Having this done, we're going to define again the load data function, almost the same way as we did in the terminal, but a little bit more verbose. Just in order to follow what we are doing, we are going to make some print statement to verify the shape of our data and to test that our function is working perfectly well. It's very important to do this with every step of the program definition. So, having this, we can already start to verify the behavior of what we wrote by testing our load data function. So basically, you can just execute the run function and you should have some print statement. So here we can see that we had a failure and it's perfectly okay because we can correct it and verify again that it is working well. Name NP is not defined. Indeed, we made again another little mistake. It's a lot easier to debug your files locally on your machine and to verify that loading your data works well, for example, before running any experiment at scale on data where the understanding of every bug can be a lot more complicated. Now that we know that our function is working well, we can define another function which will be executed by DeepHyper to evaluate our classifiers. So here we are just wrapping the auto-escalar run function, passing our load data function. Okay? Now that this is defined, we can run a search with DeepHyper. To do so, I'm gonna move to my breast cancer folder, and I'm gonna create an experiment folder. From here, I am gonna use the DeepHyper command line where you can see all of its arguments using help. And I'm gonna run an hyperparameter search using the asynchronous model-based search, AMBS, giving as argument the attributes of our package and our run function. So the problem is a problem defined inside DeepHyper. It should be, so again, you can try all of this before running any search to verify that everything is correct. You should do from DeepHyper search, HPS, AutoML, AutoScaler 1, import problem. It's saying that there is no module. Okay, so I made a mistake. Let's verify on the documentation page, for example, that it is correct. What does it say? Okay, I missed the classifier part. So here, I'm gonna try this command. Indeed, this is not a module. So we have to import it like this from and now let's print our problem, and here is printed the representation of our problem where you can see the different hyperparameters that are searched and the condition on each hyperparameters, because they are not compatible with the different classifiers defined on this line. So having verified all of this, we can execute our search. I made a wrong paste. Let's delete this and copy what we have in the documentation to make sure we are not doing any mistake. Okay, so I define my problem attribute, and now I will define my run function, which is in my package DeepHyper projects. Then it's in the subpackage breast cancer run, and it's called run. So breast cancer run. And we want to use a specific evaluator, called subprocess, with the maximum number of evaluations corresponding to 200. So the output you start to see here corresponds to the outputs of this function, and we want to maximize it. In the case of the AutoML classifier AutoScaler, we want to maximize the accuracy. Other metrics can be defined depending on your situation and what you are interested in. So I will skip this part and open the result data after 200 evaluations. Now that the search is over, I can see two files in my current directory, the DeepHyper logs and the results CSV. Here I'm not interested in the DeepHyper logs, so I will only open the results CSV using Visual Studio Code. Because I installed the Rainbow CSV extension here, I have a colorful CSV file which is very easy to read, where I can see each of the evaluated classifiers and the corresponding objective that I want to maximize. So here it corresponds to the accuracy on the validation set. Having said this, I can verify what's happening with my search, and we are very happy because we beat the initial accuracy of our baseline, having many classifiers outperforming it. We can see that the search stopped well after 200 evaluations. And now, for some more visualizations, we're gonna open this file in Sundance. So you should install this package to do these steps. Also, before going to Sundance, I didn't explain what was the elapsed column. It is basically recording the time since the beginning of the search when the evaluation was completed. So now you can do a right click on the file and you can do View in Sundance. Okay. Now that Sundance is open, we're gonna do a very first simple visualization by selecting the scatter plot, taking the elapsed for the x-axis, the objective for the y-axis, and keeping the coloration by classifiers. With this visualization, you can see which classifier is likely to perform better than others. So here we can see that AdaBoost is performing quite well. And if you put your mouse on one of these dots, you can see the corresponding hyperparameters that were used for this performance. We're gonna do a different visualization by filtering on these points. So you just have to click here on the y-axis, and then you choose to isolate the points. We're gonna apply a different coloring just to see better. By coloring on the objective, and you have a nice color map where it's easy to see the performance again. Your maximum performance was around 0.98, using an estimator's 970. Another kind of visualization you do will be the stacks plot, putting the objective in x-axis and the classifiers in y-axis, selecting color by objective and sort by objective. Thus, you can visualize in 3D which classifiers are performing better and which classifiers were then samples in higher quantities than others. So we can see a lot more AdaBoost than any other classifiers. And again, the one performing best here are located in green in this location. So sentence is a very nice way to visualize data quickly and to have a very cool render and understanding of the situation in a very short time. We're going to start playing with neural networks. Hence, from now, we're not going to run everything on our local laptop, not the search at least. We're going to test it, but not run it completely. So, let's locate yourself in the DH projects. So, I'm in the root directory of my projects. I will create another problem folder called polynom2 HPS, so DeepHyper, new problem, hyperparameter search, polynom2 HPS. I'm gonna go back to Visual Studio Code and look at this guy. I have 3 files that we are gonna use this time: the load data file, the model.run, and the program. Let's start with the load data. What's happening here? In this function, we define synthetic data from a polynom2 function. We sample randomly a set of vectors of a dimension here 10, and we're gonna sum this vector, sum the element of this vector to produce data, so that we can test a regression problem. We are returning a training dataset and a validation dataset. We are not returning a test set here, and it's important to not run an hyperparameter search or neural network search or any AutoML with a test set. Why? Because the validation set is used to help the search learn which classifier is performing better than another. Hence, if you use the test dataset instead of the validation dataset, you will bias your results. They will be better than what they should be, and you will not be able to evaluate the quality of your model in a good manner. Let's try the load data function to see what is the data shape and verify that it's working well. So again, your virtual environment being activated, you this time go to polynom2 HPS and you execute the load data function. Okay, it's working very well. Now, let's go to the model definition. In this file, we define the model. Okay. So here we are importing our packages. Okay. Here we are importing our load data function. We actually need to import it properly. What has been generated here was wrong because it was not starting from our package, then our subpackage, then our load data function. In the case of regression, we want to maximize the R square, which corresponds to minimizing the MSE, mean squared error. Then we'll have a run function taking a dictionary as argument. So this guy basically point is a dictionary. This is a Python typing if you don't know it yet. From this dictionary, we're gonna pass a number of units for our dense layer, the activation function, and a learning rate for our optimizer. And in this part, you can see the neural network definition. where you define first just the neural network. Here we print a summary of this model. After we define the loss, the optimizer, and the metric. Then we train this model by calling model fit for 1000 epochs with batches of size 64. We can reduce this guy. We collect the history, and from this history we extract the validation R square, so R square computed on the validation set, data that are not used to fit the model, and we collect the last one, because we want our model to keep learning with epochs. We don't want it to overfit and decrease. Here we define a testing set of instructions where we start by creating a point with a number of units of 10, activation function value, and learning rate 0.1. And we're going to be able to run this part to verify that our run function is working properly and that the behavior that we have is the one expected. So you can save this file and you can execute it using Python, polynomial2, and model.run. We should have a plot at the end of this training. So here is the plot, the learning plot that we have of our model for this objective. This is exactly what we want. We want it to keep increasing. It's perfect. And we have a performance of 0.28. This is what we want to do. Now let's look at the last slide, the problem. We start to import an hyperparameter problem for DeepHyper. We create our object, our instance, and then we have the 3 dimensions corresponding to the 3 hyperparameters we want to optimize. We first add the number of units, which is a discrete value in the range 1 to 100. Then we define the activation function, which is a categorical value among the 4 items of this list: norm, ReLU, sigmoid, and tangent hyperbolic. And then we define the learning rate, which is a real between these two values. We used the model we just tried as a starting point for the search, hoping that it will start and that will help it to start in a good location. Because, for example, starting with a learning rate like this is can be a better indication than starting with a big learning rate, which can create a lot of oscillation in the convergence of your model. Let's try this file so you can execute it. And we should have a nice output. Indeed, node is not a possible value, and you should replace none by this naming. Actually, you can name it however you want, and you will have to handle it in your run function. Let's check that this is working properly. We still made a mistake with the definition of the activation function in the starting point, and we'll start by advising it to use the review activation function. Now this is working properly, and we made sure that the execution of our program was okay. But if we pass this to the activation function of our model, it will fail. Then we need to modify this. So at the beginning of our run function, we can look at this key and replace it by a value accepted by Keras, which is none. You can again verify that the model.run works properly. Not waiting for the training, but just verifying that it's working well, and indeed, it's working well. Now that all of these things are defined, you can try to execute the search with the same command line that we used previously. To do so, go back to your terminal, move to the Polydome 2 HPS folder, create an experimental directory, move to this directory, and again, you have to define the problem, and you have to define the run function. Using the same kind of evaluator, and for whatever number of evaluation you want. Here we are just gonna try the search and kill it very quickly, so I'm not gonna set one. Here we have an error telling us that the model was not found. Indeed, we give the wrong path because in our folder it was model_run and not just run like before. And that's why it's always important to try it locally, because you will have all these mistakes happening during your experiments. So we modify it, and now it should work properly. It's working. The computation of the first objective will take some time, but we'll wait for it before killing the search to make sure everything is going well. And we have our first objective, so we can kill the search using ctrl-C. Okay, we are good with the hyperparameter search. Let's move to our last example, which is narrative search. So I'm again back into the root of my project directory, and I will create a narrative search problem. To do so, I will do the same as before, new problem, but instead of putting HPS for hyperparameter search, I'm going to use NAS for narrative search, and I'm gonna define the polynom2-ness problem. Why polynom 2? Because it will use the same set of synthetic data, but this time for neural network search. What is neural network search? Neural network search actually enables you to look at the architecture of neural networks in a more sophisticated way than hyperparameter search, where you have to define yourself every action of every incoming parameters of the space. So let's move to Visual Studio Code to look what is inside this folder. We again have our load data function, which is exactly the same as before. Let's try it. It's working well. The second file is the problem, and the last file is the search page. Let's first see what is an neural network search problem. So we import the neural architecture problem from DeepHyper. We import our load data function. We import the search space function. And we import the preprocessing tool, which is a pipeline of min-max preprocessing and standard scalar, which basically mean center your data. Then we define the problem using a seed for reproducibility. We give it the load data function. We tell it what preprocessing we want to do. We give the search space with an argument corresponding to a possible argument of this function that we are gonna see. We give some hyperparameters for the training of our model: batch size 32, learning rate, optimizer, number of epochs. We give it a callback so that each evaluated models, even if it can run up to 20 epochs, can stop before if it's not improving anymore during 5 epochs. We define the loss, which is here mean squared error, but it could be for classification categorical cross-entropy. We define a problem metric, R squared, and we define an objective, which is here corresponding to the validation R squared, and this keyword again asks DeepHyper to take the last one. Okay. So the linter was not showing something meaningful because our problem works perfectly. The last file is the definition of the search space, where everything is happening in this create search space function. You have to follow this template of input shape, and output shape. So here it's 1 for our data. The number of layers is an argument of this function, and it is a Keras-like API where you give your input shape, output shape. Here we say that we want a regression because we are using a specific search space, building automatically the final layer corresponding to this argument. And then we build a set of variable nodes. For each of these variable nodes, we define different possible operations corresponding to dense layer with different units and activation function, as well as the identity function. After defining these variable nodes, of course we connect them because we want one thread of our model to be direct and fixed. We'll create a constant node where we don't want to do any possible choices. We define a way of merging data And why do we define this? Because we allow in this search space for skip connections, looking over the 3 previous layers. We'll do a tutorial about this search space, giving more details. So this is just a quick overview. And here we have a test function to visualize the kind of model we can generate with it and have some information about it. So I'm going to close this file and I'm going to try to run neural text search using this problem. To do so, I'm going to use the DeepHyper command line, neural text search. You can see the different search available. AMBS for asynchronous model-based search, random search, regularized evolution. Another one is available, proximal policy optimization, but because it's using MPI, we didn't make it available directly in the command line, and you have to use the package definition to use it. It's shown in the documentation if required. So we are gonna try our neural text search. Again, making an experimental directory. I'm using the command line. We're gonna use this time regularized evolution. You don't need to define a run function this time because the pipeline is handled by DeepHyper. You define the evaluator and a number of evaluations. And we can see that it's apparently going well. We'll wait for the first output to make sure it's working well. And yes, it is. And more than that, if I'm not mistaken, we start to have, yes, neural networks that are performing better than our baseline example. Now that you know that everything is working perfectly well, you can move to data and execute these different problems at scale on the different number of nodes. Now I moved to Theta, so as you can see I'm logged in Theta, and I will start by transferring my files of my projects to this location. How can I do this? I go back to my root directory. So here I can see my DH projects, and I will do a SCP transfer using the recursive argument. And this will transfer all the files. This is done. Let's verify on Theta that we have what we want. And indeed, now it's here. Now that we moved our projects, we can install DeepHyper on Theta. To do so, we'll follow a procedure which is also available on the online tutorial. Before doing anything, let's do a module load purge. module purge. Let's load Miniconda 3 Miniconda and let's create our environment, giving a custom class and cloning the base environment. It will take some time, so I will skip this part. Now that the environment is created, we can continue the installation by activating this environment. As you can see, the prompt changed and the environment is well activated. Again, to verify, you can do which Python. Now, there is a little difference between this installation and the local installation. We're gonna to install specific compilers that are used by some dependencies of DeepHyper. Having installed the compilators, we can now install DeepHyper. Instead of giving a version, you can also install it like this, and it will automatically take the latest date, hence the one with the less bugs and more options. To finish this installation, we are gonna define a Python kernel that will be accessible from the Jupyter Hub that you can use at ALCF. A little mistake was made in this command line. The kernel is now well defined. Let's try to import DeepHyper in Python. The import is working well. Now that we have done that, we are going to define a Balsam application which is going to be used to submit jobs on Theta. Before that, we have to define the Balsam database. How to do this? Just by writing Balsam in it and the name of your database. The database is well created, and Balsam tells us to activate it. Activating a database means running it. So the server has started, the prompt has changed to show us that the database is started and working well. Now let's define the application for neural architecture search. Balsam app, name Evo, exec, we're gonna use the current Python. And we are gonna use the regularized evolution search. Execute the command, and you can see that the good Python interpreter is used because it's using DeepHyper Hands-On from your root directory, and the good application is used. To list the available application, you can do balsam ls with the apps argument. And here you find your application. Now that this is done, we can install, because yes, we forgot to install our project in our current interpreter. So let's go to DH projects and run pip install -e dot. The project is installed properly. Let's try to import it in DeepHyper. The import worked correctly. Now let's move in one other DH project and verify that things are working properly. For example, test the load data function of polynom2 working well, and test the problem definition. Everything is going as expected. We can now define a balsam job to execute a neural architecture search. So here I call this job NAS1 workshop. I put it in a workflow with the same name. I use the application Evo that I defined before, and I give arguments a bit different for the evaluator than the one I gave locally, because now I want to use balsam. Otherwise, everything is the same. I can put a given number of evaluation, of course. Let's see the recap of our job. So workflow is NAS1 workshop, name is NAS1 workshop. This is very important The workflow will correspond to a folder where you will find all the logs of the different evaluated jobs. And this name is the name of the master job, which is the search, which is going to create other jobs under the hood, other Balzan jobs. After, you can verify which application you are using, evolutionary search here, and the arguments passed to the application. Everything looks okay. So let's validate our job. Now that this is done, we can submit the job to the Theta debug queue or production queue. To do so, we'll do Balzan submit launch job mod MPI. Number of nodes 4, time 30 minutes, queue debug cache quad, project, for me it's data science, for you it should be SDL workshop, workflow filter, NAS1 workshop. You have to be very careful with the workflow filter because it will start all workflow containing this. So if, for example, you have NAS1 workshop 1, NAS1 workshop 2, and you just put filter NAS1 workshop, both jobs will be started. And it can be very problematic. So make sure that you use names that are excluding each other names, basically. And the job is well submitted to the queue. For the sake of this tutorial, I'm not gonna wait for these jobs to be executed, and I'm gonna kill it right now. I will create a DHX folder and move into it. And I will use a database where I executed the same jobs before to collect some results. This database was named DHDB-old. So when you have a job, the result will be available in this database, and to collect the results for neural architecture search, you're gonna do DeepHyper analytics parse, because we're gonna parse the logs of these jobs. I have a bit of latency with my connection. That's why when I'm typing, it's not always very smooth. My job was called NAS1 test. I'm going into, so you are in the data, you are in NAS1 test, which corresponds to the workflow, and you are in NAS1 test 86 something, which corresponds to the job, master job. You have to go in these folders. and then you select the DeepHyper logs. You do enter. And you can see some line printed telling you that this file was created. It collects 33 evaluations that have been done. And that's nice. This data file contains directly some keys that you can use. What's often interested is to know what was the best neural network found. So let's do DeepHyper Analytics. JSON, best, -n, I want the top 5 best networks, and I want to compute this on the NAS1 JSON. Cool, it worked. Now, what can I do? I can open this JSON or print it. Okay, and I can look at the first sequence. It corresponds to the architecture which performed the best, and see what is the performance. It's very encouraging because if I remember the performance that I was initially adding on my local machine, with a very simple network on these programs, we had something around 80. So we really outperformed this performance in a very short time. Now if I want to use this model somewhere else, but the model not being trained, I can select my architecture sequence. So here I just copied it, and I will use it in a Python Jupyter notebook. Now that I have this result, and I have copied my architecture, actually we'll do a bit different. Before that, we'll generate a Jupyter notebook, again with DeepHyper Analytics. Singles is generating analytical notebooks for narrative search for a single experiment, because another kind of Jupyter notebook can directly generate comparative plots for several experiments. Let's check what are the arguments. We have to give a path and a name of a Jupyter notebook. Okay. So we're gonna give the path of our data file and a name. You can give whatever you want, such as visualization. For me, I prefer to keep the default name, so I'm not giving the -n argument, and it will still work perfectly well. I do enter. Okay, the command was executed without error, and I can see that I have a Jupyter notebook that has been generated. Now we are gonna move to the Jupyter hub of Theta. To connect on this hub, you have to use the same logins information as the one you use for the SSH connection. Then we're gonna go to our DH experiment folder. I'm gonna open our DeepHyper Analytics. You have to be careful and make sure that the kernel used is the code one. So here we want the DH-env. Okay, and then we can execute it. Okay, it's working fine. Here we see that the search performed 33 evaluation and generated 33 different neural networks. You have the size of the search space and the proportion explored. It's good to notice that in this notebook The plots have often to be done carefully because they are not compatible to all the search, and depending on the number of evaluations, some of them can be nonsense. For example, here we did regular evaluations, but we have only 33 evaluations. So seeing this plot will not show any good improvement. Basically, it should show something like a random search. But still, you can see what happened and what was the performance of your models. You can also plot the objective with respect to the time as dots. The average reward per batch plot cannot work for regular evolution. It's specifically for the PPO search, which use batches of architectures per agents. And after, you have a bunch of other plots you can try. And that's it for the tutorial of the ILCF workshop of May 2020. I was very happy to present you this software, and I invite you to go to the documentation webpage, which has a lot more information than one I gave you today in the video. Don't hesitate to contact the team if you have issues with the software or errors. It is mostly supported by a team of researchers and not a real software team. Have a good day.